Hi, I'm Romain Guy. I manage the Android Toolkit team at Google.
I'm Matthias.
And Matthias and I both work on this project called Filament that's available on GitHub. It's a 3D rendering engine that supports multiple platforms, including Android, and it's used on Android and iOS at Google to run AR. So in this short talk, and we're going to try to speak really quickly, we're going to tell you about some of the performance tricks that we use to make everything run fast. So let's get started.
So while working on Filament, there was 3 performance metrics that we thought were really useful. So the first one is the instruction count, CPU cycles, and cycle per instruction. So the reason why we like those metrics is because they are very stable. That's because they don't depend on the CPU frequency or the scheduler. So that means each time you're going to run your benchmark, you're going to get really consistent results run after run. So I also would like to talk a little bit about the cycle per instruction. That's a very good metric to give you an idea of the quality of the code. So for example, if the CPI is really high, let's say above 2 or 3, that might mean that your code is running into cache misses or mispredicted branches. So that gives you kind of an idea where to look. So if you look in the Filament source code, you will find this profiler class that you can use to access those performance counters. And on this slide, you can see how to use it. It's pretty easy. You create the object on the stack, call start, run your code, and call read counters, and voila, that's it. OK, so now let's look at a few things that we did in Filament to keep good performance. So the first tip is, it might sound a little bit counterintuitive, but it's to not use the neon intrinsics. And that's because generally it will prevent the compiler from doing certain optimizations, like vectorizing loops. And most of the time, it'll do a better job than if you do it yourself. On the side of things to do, I think one of the most important things is to keep your code simple. That doesn't mean write all your code without any abstraction or anything like that, but it means that 10% of the code that needs to be fast, just keep it simple. That will help the compiler understand what you're trying to do and do a better job at compiling it. Use fast math, use restrict. Those 2 keywords will help the compiler vectorizing loops again. For those who don't know, restrict is a keyword that tells the compiler that a pointer doesn't overlap another pointer, and it needs to know that to do a good job at vectorizing. OK, so now we're going to look at an example. So that's taken directly from our math library. So here we have a matrix. We take the transpose. We transform a vector by this matrix. But we keep only one component of the result. And as you can see, the compiler did a pretty good job. The transpose operation is completely gone. It's as if it was never there. And even the matrix multiply has only the instruction that's needed for that component. If we had written the code with inline assembly or intrinsics operation, then the compiler would have had no choice but to keep that code and could not have gotten rid of it like that. This is another example. This is taken from our sphere calling algorithm. So first of all, you can see that it performs pretty well. On Pixel 4, we're doing 400,000 spheres per millisecond. But you can also see that from at each version revision of the hardware, the code is running faster. And that's not because of the clock. It's running faster because it's running in less cycles. And yet, when you look at the code, it's very simple. It's textbook my first calling algorithm. We have a loop, we go over the spheres, another loop that goes over the planes, and we check if a particular plane, if a sphere is behind a particular plane. And that's it. And because the code is so simple, the compiler can do a really good job at vectorizing it, and which in turn means that this code is scaling with a new revision of the hardware.
Yeah, in particular, this code runs twice as fast on the Pixel 4 compared to a Pixel 3, and that's probably because the CPU in Pixel 4 has more hardware to run floating point operations. So we didn't touch the code at all. It just goes twice as fast.
That's correct, yes. Now that we help the compiler, let's see how we can help the CPU. So usually what makes our program slow fall into these two categories, data access and branches. So data access because memory is slow and the caches are small, and branches because as CPUs get faster, their pipeline gets longer, and then a branch miss is costly. So one thing we can do to address this is to start thinking about our programs in a different way. Think of how your program accesses data, as opposed to think of it in terms of like the objects that compose the program. And that's what we call data-oriented programming. So here is an example. So for example, we can have a light object. It has some attributes, and maybe we have an array of lights. So now one thing to realize is that when you're going to process this array of light, most likely you won't need all those attributes. So for example, if you're going to call the lights, you don't need the direction, you don't need the color. So what that means is that this data layout is not really cache friendly. And on top of that, it's going to most likely prevent the compiler to vectorize it, because as the structure gets bigger, it might not be able to do it. You introduce some padding, which means we're wasting memory. So it's just not really good. So one thing that we can do instead is to organize the data like on the right, where you have just one structure that has all the lights, but the attributes become an array. And that, in fact, has none of the problems that we had with the first data arrangement. One thing that is interesting, though, is that if you look at the bottom of the slide, the way you access to an attribute is almost the same. It's just where the index went. But from the point of view of the programmer, it's not such a big difference, except for the fact that you can't have pointers, because there's just no pointers, there's no object to point to. That being said, this might not be a problem, because pointers are bad anyways. They are now pretty big. They're 8 bytes. That increase cache pressure, and also you rarely need that much address space anyways. So what you can do instead is design your APIs to take a container plus an index instead of a pointer or reference. And this way you sort of kill two birds with one stone, and that makes things better. This one is interesting. So don't be lazy. Lazy computation are usually counterproductive and might also be counterintuitive, but it's often the case. And we're going to look at an example, actually. So here we have, for example, a renderable object. It has a transform, and maybe we want to update its world transform based on only if it's needed. So we'd go through the list of objects. We'll check the flag to see if it's dirty or not. If it's dirty, we'll update the flag, and then we'll update the world transform, and then we finally can use it. So let's see what's wrong with that. It's about everything is wrong with that. So first of all, we've increased memory usage. Because of the padding that's added, our cache line utilization is not as good. We can't do multi-threading anymore. That test right there is probably a guaranteed cache miss. It's also probably a guaranteed mispredicted branch, like 50% of the time. Vectorization is not going to work because of the test. And on top of that, you have to write the result back, which means you're polluting some cache lines and adding more pressure to the cache. So in the end, it's probably not worth it. So it's important to use your own judgment. If the computation is really big, maybe this could be useful, but most of the case, it's not.
And so the nice thing in this case is that the fast code is the simpler code, so you're going to have fewer bugs, going to be easier to read. It's very counterintuitive because you're asking the CPU to do more work, but it is faster because these days the latency of accessing memory can be much higher than doing a few operations on the CPU.
Yeah, it's probably 20 times slower or something like that. Okay, so speaking of branches, they're bad too because each time a branch is mispredicted, then it costs about 10 cycles. That's a good number to have in mind. It can be more, can be less. But also, branches can only make your code slower. They will increase the CPI, they can't decrease it. So the best thing to do is to not have branches in the first place.
And 10 cycles, to remind you, when we looked at the numbers on Pixel 4 for the test of the spheres, that was the equivalent of 20 instructions. So it means if your branch is mispredicted, you could be running 20 computations on float
yes.
in the same amount of time.
Yeah, it can make a big difference, yeah. And so here, very simple code. We have a list of vertices. We go through the list, and based on a condition, we want to store the vertex or not. So first of all, again, that condition is almost guaranteed to be mispredicted at least half of the time. And on top of that, because the ratio of branch to code is really high, this is also a guaranteed CPI that's going to be really, really bad. So how we could rewrite this code to avoid this problem like this. You just always write the result, and instead you update the pointer based on the condition. And even though in the code there's still a branch there, that branch is actually going to go away because the compiler is able to convert those very simple branches into branchless code. And so on this version, the CPI of so its cycle per instruction of that code, of that loop, is going to be much lower. That's another example of the same thing. So this is the code you saw earlier. So as you can see on a highlighted line, we are not using branches to sort of decide if the test passed or not. Instead, we sort of accumulate the result into a variable using Boolean operations. We don't try to do early exit of the loop. And so what that does is that, again, that allows the compiler to vectorize this whole loop. And also that branch, what would have been a branch, is now just kind of a basic Boolean operation. And it is also vectorized. So we run much faster. All right. So now let's look at how we can help the GPU.
So to help the GPU, first we're going to talk about floats. So you're used to float and double, C, C++, Java, or Kotlin. One is 32-bit, the other one is 64-bit. Those are pretty big numbers, and it turns out that on mobile GPUs, on pretty much all mobile GPUs today, there is a type of float called half floats. So they use only 16-bit. And they're really awesome because you can run twice as many computations in half floats as you can versus regular floats. So either your program will run faster, or you will use less power, which is always good for the user and the battery. So how do you use that? So when you write a shader that's with OpenGL, so you have this, I highlighted the word high P. When you say high P, it stands for high precision. That means you want a regular 32-bit float. So the code here I put at the bottom doesn't matter what it does, just a bunch of random math that takes 8 cycles on a GPU I will not name when you do 32-bit floats. Now, if we change this high P to medium P, so medium precision, now we use 16-bit floats. And instead of using 8 cycles to do the same computation, we use only 4 cycles. So we are going twice as fast. And that's all you had to do. But half floats can be a little difficult to use. And to understand why, let's look at how floats work. So I'm going to use 16-bit floats. The explanation works for 32-bit or 64-bit floats as well. So we have 1 bit that encodes the sign, positive or negative. We have 5 bits. It's the exponent or the magnitude of the float. And then we have 10 bits that are the significant or mantissa. It's basically the precision of the float. And the way you use those bits is using this equation. It's not that hard. We're going to look at a couple examples. So if we look at the smallest non-zero possible number that we can encode with half floats, that's this bit pattern, and we apply this formula, that value is 0.00006. any value smaller than that will be flushed to 0. So you cannot represent a number that's smaller than this on mobile GPUs. There's something called denormals. I'm not going to go into the details. If you want, you should look at Wikipedia. So the smallest value we can encode is actually not that small. It's only like 5 numbers after the 0. Now, the largest number we can encode in half float is this one, and it's only 65,504. So it's not that big either. So we have the smallest number is not that small, and the biggest number is not that big. And we'll see why that can be an issue. And the problem, too, is like the way floats work really is that we have 10 bits of significance, so that's 2 to the power of 10 is 1,024. So between each pairs of powers of 2, we have only 1,000 numbers. So between 1 and 2, we can encode 1,000 values. Between 0, 5, and 1, we can encode 1,000 values, and so on and so on. So what that means that as you get closer to 0, you have ridiculous precision. The smaller your number, the more precision you have, because you always have these 1,024 values. Unfortunately, when you go far away from 0, it gets really bad, because you still have only 1,024 values. So for instance, if we have a float that is between 1,024 and 2,048, because we have only 1,000 values, our precision is now completely gone. Like our minimum value that we can increment by is 1, which means that if you're writing, let's say, a renderer and your unit for the world is meters, when you have something at 1 kilometer away from the origin, your smallest precision is 1 meter. That means if you try to move that object, it can only move 1 meter at a time. Or even worse, if your object is smaller than 1 meter, you won't be able to render it at all. And I will show you an example. So, we modified filament to show you what happens exactly. So this is rendering a random object. We are at the origin of the world. We're in 0, 0, 0, and it looks great. Now, if I move the object and the camera far away, let's say 1,000 kilometers away, the same object looks like this. And what you're seeing is the precision of the floats like just going away. Like we haven't changed anything else, we just moved the camera. Here's another example. This is a more complex scene. When it's at the origin of the world, it looks great. When we move it far away, look at the shadows or that Vespa right there. Like it's unrecognizable. So there are things you can do. For instance, in Filament, what we do, we actually always recenter everything around the camera, so we're always in 0, 0, 0. But I want to show you other tricks we use. So this is taken straight from Filament. You don't really have to understand this code. This is Lightning code. What's really interesting is the two high P values here. There's a comment that explains why, but basically in this particular equation, if you look at the last line before, the line before the last one, it says float B2 equals A2 divided by D2. When we looked at this code, we identified that D2 can be very small, and if it's too small, it's going to become 0, and we're going to have a division by 0. And the only way we can work around that in this particular piece of code is to force the GPU to use 32-bit floats. It's going to be more expensive, but that was the only solution. Now, sometimes you can do things differently. So here's another piece of code. We clamp our value between 0.089 and 1. And the 0.089 seems pretty random. Actually, what happens is that when we looked at our code, we noticed that somewhere we do a division by that value raised to the power of 4. Which means that and we know that the minimum value for half floats is the one we saw before. And it means that our roughness raised to the power of 4 has to be greater than this minimum value. Otherwise, we're going to have a division by 0. So our solution is to do a bit of math, figure out what is the minimum value that this variable can have so that when we raise it to the power of 4, our division will not be by 0. Here's a last example. So the way we compute lighting in the engine, we have the intensity of a light. We have something called the camera exposure. It's how bright you want the image to be. We multiply those values together, and we multiply the result by the BRDF, which is all the lighting computation. Now, here's the problem. We use physical light units, which means that a sun, like outside in California today, the sun intensity is 100,000 lux, and that's too much for floats because our maximum value is 65,000. And unfortunately, the camera exposure for this kind of intensity is smaller than the minimum value we can have. So we're kind of screwed here. Like we have values that are too big and too small. So one thing we could do is we could do this math in 32-bit on the GPU, but that's expensive. So instead, what we did is we moved that multiplication to the CPU. So once per frame, we just pre-multiply those two values together, because once we multiply them together, the result is about 3, which fits completely nicely in a half float, and then we save the multiplication on the GPU. And we're out of time, and that was it. Thank you, everyone.